Welcome back to our course in the history of mathematics. We are continuing our work in Chapter 3 of Stuart Hollingdale's book, Makers of Mathematics. And we are looking at one more application of the Euclidean algorithm. This actually comes from an example on page 50 of that book. And in that example, the author applies the Euclidean algorithm to finding the GCD of 59 and 16. And as we discussed in a previous video, this is the result of that procedure. The neat thing about the quotients that you get from the Euclidean algorithm is that if we put those quotients here like such, we get what's called a continued fraction expansion, or 59 over 16. Ordinarily, when we are applying the Euclidean algorithm, we're looking at the remainders that we're getting, but the quotients are also telling us something too. Now, there's a reason that these continued approximations are kind of useful, and I wanted to discuss that in this video. Okay, so if we kind of cover up the fractional part, we're left with the whole number part, which is 3. And if you look at the decimal expansion of 59 over 16, you'll see it's 3.6 something or other. Okay, so 3 is the best whole number approximation. Then if you look at this part, kind of covering up down here, but keeping the first part of the fraction, you would get this. And this is actually a slightly better approximation than this one was right here. To get a better approximation still, you can go down even further. And finally, if you take the last part, you would get the exact answer. So what we get from this sequence of continued fractions is a set of increasingly better approximations to 59 over 16. And you can get the continued fraction approximation for any rational number by applying the Euclidean algorithm and looking at the quotients. Now, the author also mentions the usefulness of continued fractions when we are dealing with irrational numbers, such as square roots. Now, of course, you can't get that continued fraction approximation from the Euclidean algorithm. So what I want to do here is look at an example of finding a continued fraction approximation for an irrational number. So let's try to figure out the continued fraction expansion for radical 2. So let's just start with what we know. Radical 2 is something between 1 and 2. Okay, I know it's bigger than 1, but I know it's smaller than 2. So I'm going to take radical 2 to be equal to 1 plus a little bit here. And this little bit I'm just going to call 1 over a. And then I want to solve this equation right here for a. Of course, the technique I would use is I would clear out denominators. I would multiply everything by a. So this would be radical 2a equals a plus 1. I would move all the terms that have an a over to the left-hand side. I can factor out my a and then divide to get that a equals 1 over radical 2 minus 1. And I'm going to rationalize the denominator here. I'm going to multiply both the top and bottom of this fraction by radical 2 plus 1. And that'll give me this. So that tells me something about a. A equals radical 2 plus 1. Okay, so let's play the same game with radical 2 plus 1. Let's talk about what we know. Okay, so know that radical 2 plus 1 is somewhere between 2 and 3. All right, so let's set radical 2 plus 1 to be equal to 2 plus a little bit. So we'll call that little bit b. And I want to solve for b. So we'll proceed in the same way. In fact, I can simplify this a little bit right here. Go radical 2 minus 1 equals 1 over b. And then I can take the reciprocal of both sides to get that b equals 1 over radical 2 minus 1. But if you remember, actually, let me kind of slide up a little here. That was what a was equal to. Okay, so this actually tells me b is equal to a. In other words, I have that a is equal to 2 plus 1 over a. So in other words, when I have this b right here, I could replace it with an a because b is equal to a. All right, so if we were to build the continued fraction expansion of radical 2, I would start like this. I'd say, okay, radical 2 is equal to 1 plus 1 over a. But I know what a is equal to. A is equal to 2 plus 1 over a. And then I can replace that a. So 2 plus 1 over, instead of writing an a, I'm going to do 2 plus 1 over a. And then I could keep doing that. I could keep repeating that process forever. So this is an infinite continued fraction expansion. If you have a rational number, you will get a finite continued fraction expansion. If you have an irrational number, you'll get an infinite continued fraction expansion. So here the whole number part is a 1, and then down the diagonal we would have, so we'd have a 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and keep on going as far as we wanted. Now, the useful thing there is that we could terminate this at any point and get a rational approximation of radical 2. And they would actually be alternating underestimate, overestimate, underestimate, overestimate, and the further out you go, the more accurate your approximation will be. So this is kind of the important starting technique for getting the continued fraction expansion. You start out something like this. Okay, you know what the whole number part is, so you're going to find something out about the fraction part. And then once you do that, you investigate the fractional part of the fractional part. You kind of repeat the process. So we could use a similar method for any square root, any irrational square root. We could find a continued fraction approximation in a similar way.